All right, we are recording, or we'll give it 12 seconds. There's a 12-second lag.
All right. How many people?
Okay, you're live now.
Okay. I don't know. Maybe we want to wait a few minutes for more people to join. They're going to join.
Yeah, let's wait. Let's wait a couple of minutes. It's only 6 o'clock, so I'd give it about 3 or 4 more minutes.
Good. All right.
Okay. So were you guys at Garvey last night?
Yeah, we had very few visitors. We had a family come by. They stayed for about 5 minutes, and the kid was not too terribly interested in everything, but talked like crazy. It was funny. And we had a couple of people there who were interested in learning about the tools we were using. I think I see Eric Patterson there, so on the group here. Hey, there you are. He was there when we were talking about just what we're going to discuss tonight, the basics. One of the things that didn't really get mentioned during the presentation on SharpCap was that there is a pre-processing function that is available on the version 4 of the tools, which is pretty stable as far as I'm concerned, but it's still considered beta. And the tool has the property that it will do some rudimentary extraction of light pollution, so that when you see the object in the camera on the screen, it will have subtracted out probably 90% of the light pollution, so you can actually see the object while it's coming up out of the noise. It's kind of nice.
Wow.
And over time, as it stacks, you can see the graininess reduce a little and a little every time it averages another sub-exposure into the fray. you'll see one of the examples tonight of an image we took. I think it was January 19th, M1. And we had some lunar problems there.
Water problems?
Lunar problems, whereas in full moon was rising as we were taking the image. I was surprised how well it did, because M1 is an extremely low surface brightness object. It wasn't a great image, but I was surprised we even got it at all. Some of the stuff we shot last night, I'm not sure we're going to be able to extract much out of it, but it was fun to try. It's not a case that we had a bunch of people that really wanted to see stuff. After the family left, we moved on from M42 and just kind of played around to see how far we could push things.
The image you got of N1, is that the one you posted that had 271 10-second exposures?
Yeah.
That just blew me away. I never, and that's the one thing that I've never really been able to get my head around, is the trade-off between duration of the exposure and number of exposures.
Well, theoretically, barring any other consideration, and there are some really serious ones, the equivalent, I mean, you could theoretically take a half-hour exposure of an object in one shot, and theoretically could get an image if there's no light pollution. But the risk of doing that and having it ruined by an airplane fly through or something like that, especially at Garvey, is not worth it. So theoretically, you could take 271 sub-exposures of 10 seconds, or any interval even smaller, like a 1 second exposure, and 2070 exposures or something like that. Theoretically, that would be the equivalent result, but it won't be, because the cameras have what's called read noise, and it's a noise that occurs when the pixels are read out. And you can't do anything about it. You can't even calibrate it out. So you're stuck with that as a noise floor. And it's something in the order of 1 to 3 electrons in the pixel or root mean square that you can't do anything about. So if your image is faint enough and its photon collection falls in that range, you can't distinguish it from noise.
So how's that? Is that the bias that you're subtracting out when you take
Worse than the bias. It's pure noise that you can do nothing about. The bias I mentioned in the summary is the effect of the light pollution. Why don't we just get this thing started?
Yeah. Okay.
We're going to get off track here fairly quickly. So I have a small number of slides here to kind of set the stage, what we're doing here. So we're going to be talking about 2 pieces of software that are free for doing image processing for deep sky imaging. SiriL and Gimp both do similar things in that you can manipulate images, make adjustments, do brightness stretching, etc. SiriL, it has buried within it a tool for measuring the brightness of the light pollution and subtracting it out. That's key to this whole process. There's a lot of processing tools in SiriL that are useful for everything that Gimp does, but Gimp has some interesting other things available that we will discuss a little bit later. So we're going to go through kind of a step-by-step workflow. This workflow is one example of what you can do. It is not all-encompassing. As you go along, you will find ways that optimize things for you specifically, and you may find a new workflow that might work better. So let's go to the next discussion here. So what it is to get started? Started in 2016 when I thought about the physics of what's going on in digital cameras, and realized that the sensors are linear devices. That is, if you put in a quantity, you get a response of a certain amount. If you put in twice the quantity of light, you'll get exactly twice, not plus or minus, exactly. That's the pixel response characteristics. Now, there's nonlinearities that can occur as a result of the read amplifier that takes the data, in other words, reads the charge that's in the picture element after the image is exposed. And so over certain ranges, that read circuit, that read amplifier, if you will, might cause some nonlinearity, but the pixel itself is perfectly linear. So I figured, well, I'll test it on something challenging like Rosette Nebula. And I took some pictures of with a DSLR. I calculated what so-called unity gain point is for the camera, and set the ISO number in the quote unquote film speed. No film, of course. And just got a bunch of images. I had some 40 some images of, if I remember correctly, it's 4-minute exposures each. And then I used Photoshop to remove the light pollution with a rather clumsy methodology. That was to use a Gaussian blur function with a 400 pixel radius, which essentially turned the image, the raw image, into a pure gray or pure colored, if you will, representation of the light pollution. It smeared out everything, the stars, the object, etc. And I used that as the basis for subtracting out the light pollution. And it worked, much to my pleasant surprise. Unfortunately, I found out when I tried it on M42, it did not work. That's because the Rosette Nebula is a very flat brightness range versus M42, which has an extremely broad brightness range. And this method of blurring it out to get the light pollution image did not work. So about a year later, I was involved with stuff at Garvey. And we were stacking images from our nice new ASI 071 imaging camera. And I was trying to find ways to process those images. And in a web search, I found that PixInsight had a tool called dynamic background extraction, which set down sampling boxes on the image, measured the light pollution in each of the boxes, constructed a surface that represented the light pollution in each of the 3 color channels, and then subtracted it out of the image. It worked really, really well. And it didn't matter what brightness range the images had, as long as you followed certain rules. And we'll discuss that as we go along. For Garvey, we were stuck with 10-second sub-exposures for a lot of reasons. The biggest reason being the mount is some 45 years old and has a 93 arc-second peak-to-peak periodic error. So if we took longer exposure, we'd have nothing but trailing stars. And that, we found that 10-second sub-exposures got us some 80 to 90% of the images without any trailing stars. And that was good. But when I described what I did to people in the club, the sticking point was PixInsight. PixInsight has a license fee of some 230 euros, or about 270 US dollars. And it's a bit of a steep climb for someone who's just starting out in astrophotography. So I thought, that's not fair. I mean, I've been in astrophotography for almost 40 years, and I wouldn't think twice about spending the money because I want to get better images. But if you're just starting out, that's not the way to do it. Your hobby is expensive enough without having the tools cost a fortune. So during the pandemic time of 2020, I did some more research and found a tool called SiriL. As you see, it's kind of a funny spelling, SIRI, capital letter L. The origin of that is the group that built this software. It's actually an image processing tool. that was based upon some earlier tools called IRIS, IRIS. So they turned it around, added an L. I don't know the history of that. I didn't pay attention to it. But it basically performed all the kinds of things that we needed that was done in PixInsight with the DBE. So that was good. Now, there were some control parameters in PixInsight that were giving you a little bit more control over things, but we're not going to dwell on that. It's good enough. I'm pleased with it. Gimp is a tool that is very, very similar to Photoshop. Again, I abandoned Photoshop when they went to this rental plan. I didn't like the idea of having to pay a monthly fee to use the software. If I was a professional photographer, that might be different, but as an amateur astronomer, no, I didn't want to do that. But Gimp had been built for the past 15 odd years to duplicate the functionality of Photoshop. So this is another free tool that allows us to do the image processing that we're about to do. Excuse me, I'm still having an allergy problem. So here's the game. We're going to do imaging in a severely light polluted environment. My backyard is designated Bortle 8, which means from my backyard, the sky brightness is something like 18 magnitude per square arc second. Garvey is a little bit worse than that, but made much worse by the ball field that's right next door. So it's close to a Bortle 9. And again, it takes advantage of the linear properties of silicon sensors. We're using CMOS primarily. If you have a CCD, it'll still work. And in fact, if you have a DSLR, that will also work. Once you've stacked the images, whatever tool you're choosing, for example, Deep Sky Stacker will take the raw images that come off a digital single lens reflex camera and stack them quite nicely and preserve the linear characteristics of the raw data. The nice property of this methodology is something between last quarter and first quarter moon have no impact on the ability to do deep sky imaging. It doesn't add enough to the actual regional light pollution to make any difference. But you must keep in mind that when you're imaging the deep sky object and the light pollution has photon arrival noise just like the object itself does. When you subtract the light pollution, you remove what I had mentioned as being a bias caused by the light pollution, but it does not remove the noise. There's nothing you can do about that. So don't give up your trips to dark sky, but it certainly gives you more imaging time, especially when you're stuck at home with something like COVID going on. So again, light pollution is treated as simply a bias. In fact, most of the camera control software packages allow you to add a bias to your image so that your histograms for the actual imaging object is not pressed up against 0. And that's useful when you're doing stretching operations to avoid having parts of the image not stretched the way you intend it. Light pollution has color. You must get rid of that color because it will imprint onto your deep sky image. If you just clip the brightness of the light pollution and don't fix the color, the light pollution color will change the color of the object that you're photographing, and you can't control the color balance. The other thing light pollution has is gradient. You will normally be doing dark frame subtraction and flat field correction in your images. Those two functions must be done. Don't skip it. But the gradient will come up and be a problem, and we'll see that in a moment. And in the case of, as I mentioned before, SiriL removes the light pollution gradient, but leaves the bias in the image. And the reason it does that is it's designed to work with people that work with color filter deep sky imaging. It's luminance, red, green, and blue. So it treats the three color channels and the luminous channels as separate entities and performs the light pollution removal on those alone. And that leaves the color of the light pollution unchanged. That can be fixed, as you will see. So the gradient is going to be a problem, and we'll see what that looks like in a minute. So here's an example of an image we took at Garvey some year or so ago. I forgot when we actually took it now. This is the raw image as it comes off the camera, light pollution and all. You certainly can not quite see the object in there. The thing I'm going to point out here, and if you have a decent telescope drive, you're not going to have this problem, but you see this band on the upper edge and the right edge. This is the drift that occurred during the time this image was being stacked. If you look very carefully, you'll see banding in here. It's darker here, a little bit less gray, and a little bit less gray here. Those bands represent the effect of the periodic error in the right ascension drive. So when we're processing the images, we must find that imperfection along the edge, if there is any, and crop it out before we do any processing. Because if we don't, then the light pollution removal will do a lot of extra work to get rid of that, and that's only going to corrupt your image. So there's the resulting image from that. Not too bad for a severely light polluted place as Garvey is. So here's an image taken from my backyard of M31. Used a 400 millimeter telephoto lens for telescope, if you will. And I did not do a complete extraction of everything to do with the light pollution. I just did the subtraction, but I did not do the gradient removal, just to see what would happen. And you can see there's brightening in the lower left corner and dimming in the upper right corner. And you can see kind of a reddish, kind of almost reddish greenish tinge to it. My delightful neighbors like to illuminate their trees with lights at night. So my sky has a slightly greenish cast to it. So there you are. That's what happens if you don't remove the light pollution and its gradient. So if I remove the light pollution and its gradient, this is what you got. And I made a mistake in this particular image. I had replaced a flat field image with a better one, and I forgot to switch to it. So I've got a little bit of dust donut effect here caused by the correction that was done with the old version of the flat field. All right, this is just a couple more slides now before we get started. So here's one of the more recent images we took from Garvey. This is M1. At the time this image was taken, M1 was almost at zenith. So the effects from the ballpark and all the other light pollution were as small as it can get for that particular site. You can probably barely see it here, but there's a blue peak, a green peak, and a red peak. This represents the color characteristic of the light pollution. You'll also notice that all of the data is in the lower roughly 10% of the dynamic range, which is represented in the horizontal axis. So we're working with an awfully small amount of data here. And that's why when you save images from stacking, you must use 32 bits per color so that you can preserve as much detail as possible in what's left. Okay, so here's a look at what we're going to be doing. I cropped into this histogram of M1. You see the blue peak out here and the green and the red peak. This is the raw data showing the light pollution. This is the, if I were to apply background neutralizing, the color neutralizing, you see now all the color peaks are lying one on top of the other. And if I take that image and I stretch it, you'll see that it's pretty much the same alignment, except we're getting a little bit of a right direction shift of the blue, and that's another detail. We may or may not have to correct for that depending on the image circumstances by applying another cycle of background neutralization. Okay, so let's look at some facts here when you're doing imaging in urban environments. Every backyard is different. Every site in an urban area is different. And every site in every urban area varies with time, depending on what time of day at night it is and what direction you're pointed the telescope and so forth. So here's some examples from images that we're going to look at. This is, again, M1. We had a 95% illuminated moon that had just come up when we took the image. Some of that blue is due to the blue sky caused by the lunar illumination. If you take a deep sky or a long exposure with a wide angle lens of a scene when there's full moon, you'll find that the sky is quite blue, just like when the sun's out. M42 is another image. This was taken with a 15% illuminated moon, some 35-degree elevation above horizon, unfortunately near the direction of the ball field. And you'll notice two things here. These peaks are slightly different in their positions, and they're broader. And partly they're broader because M42 is a very bright image, and partly because we had a lot more light pollution looking over the ball field. So there's more light pollution gradient there than there was in M1. M31 in my backyard, there was no visible moon above the horizon. It was taken at an elevation of 70 degrees. And it was also in a northerly direction, in the direction of where it's darker than if I point southward. And again, you see sharp peaks here. The blue peak is closer to the green and red peaks. This is the difference in our particular situations for the regions that we've been looking at. Everyone will have a different experience here, but all these tools that I'm going to be talking about will deal with that. So that's this portion of the discussion. I'm going to close this out. We're going to start up SiriL, and we're going to start going through the process. Come on. This is the latest version, 1.00-RC2. This is a designation they added recently. This is the latest version. They've been making changes that have fortunately been making this a better tool. So let's explore the desktop here. The most important thing, of course, is open. It'll let me bring up an image. This little icon here lets us set a working directory. And what I'm going to do is choose, this is the working directory where we will save the images. If you don't do that, don't worry about it. When you save an image, and by all means, don't just click save up here, because if it does, it'll overwrite your image, the original image. That you never want to do. No matter what processing you do, you never want to overwrite the original image. In fact, what I do is I keep two copies of it, one in the directory in which I'm working and one in an offline hard drive, so I can't ruin the original image. There's an icon here that says save the current image to a different name. This is what you will use. So you can always change the name of the image file. What I do typically is I use a string of abbreviations to indicate what processing I'd done before I had saved the image, so I can at least remember what I did. I also keep a notepad nearby and I write down everything I do so I can repeat it if I need to. I'm a little bit fussy that way. I do the same thing when I take the images. I write down everything, even if I get up to go to the restroom. I mark that down because sometimes set up locations. If you're like in my backyard, I'm set up on a pad of concrete. It wiggles when I get up. So I need to make a note of what time that was, so that if there was anything wrong with the image, I can fix it. Okay, so let's open the first image. What did I do here? Okay, here we go. Okay, so I've already cropped the image in a check here in my original processing on the thing, but I'm going to open the original image just so we can see what it looks like. And funny thing, you don't see much. And the reason for that is, as you saw from the histogram, the majority of the image is down in the lower 10% of the dynamic range. This is a 32-bit per color image. There's not much to see here. Even the light pollution is below everything here because of that huge dynamic range. But there's another useful tool here. Down at the bottom, if you look where the cursor is, there is a list of screen processing functions. It does not affect the actual image itself, but it changes what you see on the screen. So it normally comes up linear, as you see here. I can go and click histogram, which is the first step I would do, and you can see how ugly this thing really is. It brings up everything, including the read noise and all the crazy gradients and all the banding that's caused by the drift and all that stuff. So we're going to start here, because now I can see where the drift has occurred, and I can crop out everything that is not what I want to play with. Since the object is fairly small, I'm going to be a little more liberal in the clipping. So I'm going to draw a box that goes inside all the drift lines. I'm going to give it a little bit extra just because I can see a little bit of gray down here that I don't like and a little bit over here that I don't like. You can adjust each of the boundaries separately because you can get the cursor to give you the individual adjustments. Okay, so now I've framed what, let me just change the upper one. I don't like that either, down to here. Okay, so now that I've framed the image I want to process, you right click and you go down the list and it says crop. So now I've cropped the image. You knew what that is. That's a satellite. Sorry about that. We'll crop it out because this is a small object anyway. So now, another thing to remember is SiriL works on individual color bands, red, green, and blue. So if I go to click blue, the image changes ever so slightly, and click red and blue, it gets a little bit more bright in the background. Remember, the blue had a brighter position for the histogram, so there was a lot of blue light in there. SiriL likes to process individual color bands separately. And that's fine, we can work with that. So we've done a crop. The next thing I'm going to do is, no, these steps I'm doing now are in linear space. As soon as you do any stretching, the image is no longer linear and greatly complicates some of the things that you might need to do in a linear space. Cropping is one of them. You want to be able to see everything you can, and that's what that histogram stretch does. The other thing is you want to be able to control the background neutralization and also the background extraction. These are all linear operations. You want to do those in the linear space. So first thing I'm going to do is change the screen stretch. The arc hyperbolic sine stretch is a kind of nice natural stretch. You can see the object dim in the background. You can see the light pollution. That's kind of the right ratio. The other thing it does is it brings up a lot of the dimmer stars. So what we want to do is select a region where we're going to do the background neutralization. And notice this is a slightly bluish gray, okay? So now I'm going to pick a little region like here. I'm going to draw a box. there are no significant bright stars, significantly bright stars in there. You can see most of these stars are the brightest ones in the field of view. So I picked a box. I'm going to go to image processing. It brings up a list of image processing options. I'm going to go to color calibration. That brings up two options. One of them is photometric, which we're not going to be doing because we're not doing brightness of star measurements. Color calibration, this window is where we're going to do the background neutralization. This box represents the area where it's going to take the sample of the color of the light pollution. So we have to tell SiriL that in each of the color bands to take the information it needs from here. Okay, so I've got the red band selected. That's what we're seeing here. I'm going to say, I'm going to left click, use current selection, and it shows the coordinates of the box position. Next, I go to the green and I tell it, use the current selection. Next, I go to the blue and say, use the same selection. Now I click background neutralization and the work gets done. Notice it turned more neutral gray. That's the first important step that we needed to do. So it's no longer that kind of slightly bluish background. So we close that. The rest of this window, it does other things, and we're not going to get into that here because all we're doing is getting the light pollution under control. Okay, so there, we've got that done. I went back to the red band just for fun. So I'm going to leave it in this hyperbolic sine, arc sine mode. And now we're going to look at doing the background extraction. So the background extraction is down this list of image processing options. We left click that, brings up a little window here. Here are the parameters involved with that. There is a tolerance function here that tells the background extractor what range of brightnesses you want it to look at. Ideally, you want it set to a point where it doesn't see the stars, that it doesn't place samples over the stars, and doesn't place samples over the object itself. Okay. Samples per line, I typically leave it at the default of 20. That's usually enough. If you have a really big imager, sometimes it's worth going further. Or if you have a steep gradient, it might be useful to go to a larger number of samples to get a better accurate representation of the gradient. So now we click generate, and it puts down a bunch of little green boxes. And you go and scan along and make sure that none of them encompass any of the brighter stars, and they don't. If it clips a really faint star, it's not going to really bias the results that much, so don't worry about it. However, in the range near the object itself, I don't like this pixel here, this sample, and this sample. These two are a bit too close for my comfort, so if I right click on that, it gets rid of it. Okay. And sometimes if the object has a lot of nebulosity, faint nebulosity beyond this range here, I would go around and create a guard band that's even bigger. I'd remove this group of samples as well. But M1 is fairly well confined to a little region there. So we'll let that go. Okay. So now we've set everything. So now I click apply. And it does its magic. What? There's no difference. That's because it has processed the individual bands, gotten rid of the gradient, and has left a bias now, quite linear, that represents the color brightness of the original image. Why did they do that? I'm not 100% sure, but it's not a detriment. So we're finished with this. and we close it. So now I go back to the linear world. This is where the fun starts. At this point, I'm allowed to click RGB, which shows the true color image. Notice there's a nice orangish star here. So we know we're in the color mode. In fact, these two stars are also kind of orangish, so they're fairly low temperature stars. So we got this 32-bit dynamic range. And now we want to bring that lower 10% of the brightness of the image up to where we can see it. So we go to image processing, and we go to histogram transformation. If that looks familiar to you, that's exactly where I got those images of the histogram that we were looking at early on in the presentation. Notice all the images confined to a really narrow spike here. And that's where everything is. Everything from the histogram to the left is light pollution. Everything inside the histogram and a little tail, which you can't see running along the baseline, is the brighter star data. There's a box here. If you click it, it causes this vertical scale to be logarithmic. So now you can see the extreme tail of the histogram showing everything that's out there, the brighter stars. Somewhere in here is where the actual image is confined, and so forth. You can leave it on if you want. I prefer to just go back and let it be linear. So there are two controls here. There's a black point, which is right here at the far left. This represents the transfer function of this brightness to the brightness at the output of the histogram transform function. Okay. So I'm going to grab a hold of this mid-band point. This is the mid-range. You see that's halfway between the extremes. And I'm going to drag it. Come on. Drag it to the left. And you see the sky's gotten brighter, and you can see a little bit of the image in there. Now I'm going to drag the black point and move everything back to the left. So I've pulled out more of the light pollution. Now here I have to explain something that's fairly important. Do not attempt to take another cycle here. Pull this again to the left, this again to the right, until this histogram spreads out more to show the image. If you do that, you're going to create a situation where you're going to get greater and greater difficulty trying to get a good balance of stretching. So a good policy is to stop here, click apply, and now we're back to the linear regime with the stretch that you've just set. So we do this all again. Drag this to the left, drag this to the right, dark, we get a little bit more of this guy here. Notice the histogram is getting wider. So we are starting to stretch the brightness so that we're going to be able to see the actual object that we've photographed. We click apply again. And again, we do the same thing all over again. Left, come on, it's a little bit tricky, to the right. Now we're starting to see a bit of our target here. So we click apply again, back to the linear world. Drag it, and we drag it again. I'm trying to avoid getting into all the way into the histogram right now. You notice I haven't gotten into the left edge of the histogram. This is mostly light pollution here. I'm just sneaking up on this slowly because it's too easy to overrun things and clip out important stuff in the image. So you got to do it a little and a little. So we apply. Now we do this again. Now we're starting to see the histogram get to where we're going to see something. Come on. Okay. There's M1. You can see some of the color structure in it. We'll crop into this later when we get into Gimp. But now we're starting to see a whole passel of stars in there that we had not even been able to see even when we did the histogram stretch on the display. So we're going to apply again. And I'm going to be bold, and I'm going to do one more shot here. I get into here, into here. I'm going to leave a little bit of gray in the background because we're going to deal with it. Notice the blue peak declined because I've clipped some of it off. We know that was light pollution, so it's not a big deal. Okay. If it was a case where we were in some very dark area and we started to clip the blue, you might kind of want to back off a little bit on that. But for here, remember, you know what? If you've been to Garvey, you know exactly what it looks like there. It's really bad. Okay, so we click apply. Now we've gone about as far as we dare in this mode. So now I go over here and I click on save with a different name. Okay, so I have SiriL Gimp processed. The original file name is stack 32 bits, 271. This is 2,710 seconds of stacking. So I'm going to say M1 underscore to identify this thing. And at the end of this to identify it underscore SiriL. And by that, I mean, oh gosh, I did that. Hold on a second. I clipped off this thing. Okay. And I know all I've done in this case was the background neutralization, the background subtraction, and the histogram stretch. And I would write that down on the notebook, not necessarily putting it in there. But when I enter SiriL as the first processing step, that's the standard series of steps that I would do. So we're going to save this now, since we have stretched the blazes out of it. I'm going to go to a TIFF file, because if we stay in FITS file mode, which is the professional standard image format, most ordinary image processing tools like Gimp, Photoshop don't do well with that, especially 32 bits. Right now, Gimp has just been updated to handle 32 bits, but that's a bit squirrely right now. So I'm going to save it as a TIFF file. So just to mark that so I know what I've done, I'm going to TIFF just to indicate that that's what I've done with SiriL. So I'm going to save that file. And now it automatically comes up 32 bits because that's what it was. I have to click the button that says 16 bits, so it'll make the conversion. Okay, so we've saved this image to a format that we can play with in Gimp. So we're not going to do any more here for the moment. And so I'm just going to close this out. The reason I'm going to do that is this burns a lot of memory. So we want to just get it out of the picture for now. I have 16 gigabytes. I could have left it there and I could have gone on and done a couple of other things and run a couple of other tools. But if you don't have at least 16 gigabytes of RAM, you might run into problems. So we're going to launch Gimp. And don't be deceived that it sometimes it's really slow if you're on a hard drive. I have a solid state drive. So we're going to open the file in the external drive. Where are we? And Gimp processed, and this is the image we just looked at. So we open that. And it asks to make sure you will allow it to set the color profile to match what's in Gimp. I prefer to do that because when I set up the cameras, my cameras and the one at Garvey, I always balance the camera's color temperature for solar so that you see the image as close to natural as you would see it if you could see it in color, which you can't, of course. So I'm going to click view, zoom, come on. I'm going to say fit in the window so we can see the full image. So I don't like the satellite. I'd like to get rid of that. In fact, it's a small object. So I think what I'll do is I'll click the cropping option, and I'm going to crop this down to something significantly smaller. Like that. Okay. So we click image, crop to selection. I'm not going to go through all these controls with you specifically. These are very similar to what you have in Photoshop, if you're familiar with that. And this is very similar to what you have in something like Lightroom or many of the other general image processing tools. So if you want to keep notes of what we've done here, fine. But in this case, we want to let this kind of go as easily as possible, minimize the number of complications in the talk. If you want to go in more detail about processing in Gimp, because I've made the transition from Photoshop to Gimp, we can make that a separate session. But now I'm going to click view again. I'm going to fit it in the window so we're back here, and you can start to see structure in the object. And you'll notice in here, there's what looks like kind of an elongated star. Let me zoom in a little tighter here. Okay. It's like two stars. You see a little bit of a brightness here. That's the synchrotron radiation caused by the neutron star. So we got lucky. We got that. So what do we got here? We've got a lot of noise in the background. If you can look, if you can see it from your screen, it's kind of grainy. In fact, let me zoom in enough to bring it out. You see how grainy that is. Also, there's a little bit of drift in there, but that's something to do with that ancient clock drive. So there's a lot of graininess there. There's a number of things we can do. One of the things that I would suggest, just for starters, is to select the curves tool. There's the histogram of the image. That's the general distribution of all the colors. Again, we have sliders. This cuts off what's left of the light pollution in there, and that's what's to the left of the histogram. We have a slider here in the middle that represents the center point. We're going to do the same thing we did in SiriL. We're going to do a darkening. I'm going to stay out of the histogram for the moment. Make sure that that point is all the way down to 0 in the vertical direction, because it will leave a bias. And then I'm going to click here to set a sample point. And I'm going to bend the curve just a little bit as we go. You still see the noise in there. Now it's even more apparent. Okay, but we've gotten the brightness of the object up, and you can see that the noise has imprinted on the object itself. We got decent saturation in there, but it's not great. So I'm going to click OK and save that. Now we're going to do something that is a little bit odd, but it works for the kind of thing we're doing at Garvey. There are filters, just like in Photoshop. There's a blur function, long list of a blur function. Down the list here, in one called median blur. We're going to select that one. Median blur has an interesting property. It takes whatever pixel it's on, looks, in this case, you see radius of 3. It looks for 3 pixels all the way around a given pixel. It then calculates the median brightness of all the pixels around the one where it's sitting and assigns that value to the pixel. And this function slides through the whole image, and you'll see what happens here. Let me unclick preview. You see the graininess? And it's gotten more muted. That's a good step. So we're going to click OK for this. Now we go back to curves. And let's see if we can clip off more of that grainy light pollution stuff. And as you can see, there's more room to work. You'll notice also the histograms become a bit unsymmetrical, a little bit steeper here than it is out here. That's because we have a gradient of brightnesses. We're going to slide into the histogram a little bit to darken the sky, but minimize the effect upon the nebulosity. I'm going to click preview, click the button to remove preview. You'll see where we came from and where we've gotten. Okay. I can put a point on this graph. I'm going to do that right here. I'm going to pick up that point and brighten things just a little bit in the nebula. And then I'm going to slide the dark point a little bit further. So remember, everything to the left of this point right here becomes black. Everything to the right becomes stretched by this curve. So what we've done is we've stretched fairly close to the brightness range of the object, which is mostly on the trailing edge of the histogram. You see we're past the peak on the histogram. So we're dumping the last bit of noise from the light pollution. Notice also there is still imprinted noise there. There's nothing we can do about that. So I'll click OK. And then we'll go back here and zoom to fit in the window. And that's what we've got so far. One of the things I like to do, it's your choice, but I go to colors, I select hue and saturation. I like to artificially boost the saturation a bit. That's my preference. You can do whatever you want. And boost it up a little bit to get a little more red, a little more color in the stars. You see with the saturation boost and without the saturation boost. It's not a lot, it's just enough to make it a little more well-defined. So we click OK. So here we are. We can call this a finished image if you want. There is another processing step we can do, but it uses another tool that I didn't mention in the outline because it's not a free tool. It costs, it has a license fee of $42. It's not expensive. I have it because it has some neat sharpening functions in it that will make this image really nice. You'll see it a little bit later. So what we want to do is save this thing. I'm going to keep it in 16-bit world because we want to preserve the full dynamic range. So we're going to export. If you don't export, then you will get the Gimp file format in the save. That's not too bad because if you're going to continue processing it later, you might as well have it in the format this thing understands. But I'm going to export it. And I'm going to label this that I have done a Gimp run on it. And I'm going to keep it in a TIFF format. And so that's the default because that's what I started with. So if I export it, and you just typically click export, there's some choices here for compression. I don't think you want to do any of that. This is a fairly nice compress function. It is image quality preserving. It does not detract from the image in any way. It can be reversed. JPEG does some really weird processing that can leave some artifacts you cannot get rid of. So you don't want to be in JPEG unless you're going to send the image off somewhere to be shown. We're going to export that. So we will close out this guy. Oh, by the way, you notice this window popped up, says discard changes. All that means is you have a long list of, click that out, start again. You can see your full history of what you've done here in Gimp. You did rectangle select to crop the image. I did curves, I did median blur, I did curves again, then hue and saturation. If I want to undo this right now, I can do that and go all the way back to here and go all the way back to base image that came in. All this is preserved. And if you save it in the native format of Gimp, you will preserve all of this. But I'm not interested in doing that here. So I'm going to go back and finish the export. So, export. Oh, I'm sorry, I did that already. All right, so now if we look at the accumulation of processed results, here's the image we just processed with Gimp. So close this out, discard changes. Are there any questions at this point before I go any further? Okay. Now this other tool that I mentioned, I'm going to show you what it can do, but this is purely optional. It's called AstroImage. I'm only going to do this once because it's detraction from what I want to do later. We're going back to this thing, the processed image. Here's the fully processed image. We're going to open it up. Now, the nice thing about this guy is there's an enhance tool here called multi-scale contrast. And it has two parts to it. There's a window here that shows a portion of the image. I'm going to try to get myself over to here where I can see the actual target itself. There's a group of sliders here that enhance detail at various scales of the image. Near as I can tell, what this thing is doing is some variant on a processing function called wavelets. It's not the same as what's it called? My brain turned off.
Registax?
Registax has the full wavelet. What I'm thinking is, unsharp masking. So if I make some adjustments here, what I'm going to do is try to enhance things a bit more in the image itself. Okay, so there's the original image. Here's the processed image. I'm going to click reset all. Watch carefully what happens in here. Reset all. You can see what happened. It gave us more details in the center. You got to be careful of this because any of these adjustments can be done such that you end up with something that ain't there. It does enhance the noise a little bit, but at least it shows more details in the core of this thing where it's more buried in the synchrotron radiation in the M1 structure itself. I'm going to click OK and let it do its thing. It's a fairly processor intensive task, but you can see now a little crisper. There's still noise in there, but okay. So by way of example, this is one of the things that can be done with AstroImage if you want to use it. You can do something that approximates that in Gimp, but not quite as selective. You could even take the image into some other tool that has wavelet processing and play that game. So now I'm going to save this.
Is there a way to get rid of the blue halo around the stars?
Yes, there is. And the way you do that is in SiriL, there's a function that will allow you to find the stars and mask them from the processing steps that follow. So if you do that and you select the parameters correctly, you'll select all these brighter stars that have the halos. And the halos there, by the way, that's because of the optics of that little black telescope that's at Garvey. It is not an apochromat. It's a doublet f8 telescope. So the focus on the blue is not quite right. So if you were to mask out the brighter stars, and you can see those quite clearly in the image as you go along in the stretching process, you can bring up the brighter stars, you can go through and select the star images, set the parameters to select only the star images, and then do the stretching that we did. It'll bring up the fainter stars, which don't show the halos because it hasn't stretched the brightness spike of the star enough to reveal the out of focus part of it, and you'll get rid of the halos. So all I'm going to do is change the file name here again to AI. Let's say contrast. Okay. And that saves that image. So that's basically it. We want to take this to saved as a 48-bit color because that's what the original 16-bit was. No compression again, and save the file. Now, if you want to generate a JPEG image to post somewhere, you can go back into Gimp, pull this image in, do an export as JPEG, and it'll come out with a much, much smaller file. I'm going to close that out and go back and review what we've got here. So we've got the original image that had been processed in SiriL. Notice it's a fairly good sized file, but not as big as the original file. The original file was 190 megabytes, but we've also cropped out a lot of stuff and reduced the noise in the image, which compounds things. So we can view the images separately if we want, but that's the final result. Not a great image, but it's better than you would ever hope to get in a severely light polluted sky. Okay. How are we doing on time? 7 o'clock. Let's kind of take a poll because I don't think we're going to have time to do all three images. We could either do M42 from Garvey or M31 from my home backyard. Is there any opinion one way or another? I guess everybody.
I'd like to see M42 since it's got
See,
such a high
M42.
dynamic range.
Okay, M42 is what we've got. Okay, we'll do that. Dynamic range is a good point. So here we go again. So I only have 135 stacked images here. Because remember, we had Garvey, we had visitors. This was toward the end of the evening, not many visitors around. We were allowed to spend a little time to play. Okay. Go away. So we're going to take that into SiriL and start this process again. So we open. Back. M42. And by the way, one other thing with SharpCap is you can save images in 4 different versions. 16-bit fits if you have a tool that doesn't tolerate 32 bits. 32 bits fits. And then there's the processed images that you saw on the screen. And I'm going to use the 32-bit because it gives us the most to work with. I'll pull that in. Now you can see why I had trouble with this when I attempted to do it in Photoshop. The core of the image is starkly bright in the linear image. That means it's filled the dynamic range of the 32 bits and more. Put a little color in it, you can see the trapezium is totally burned out. You'll never get an individual image out of those 4 stars at all in this thing. It would have taken something like a 1 to 2 second sub-exposure, a bunch of stacks of that would show these 4 stars, and then you would blend the 2 images together. We're not going to go into this here. That's a whole different game. So we're going to start this thing the same way we did the other. I'm going to go to the linear, pick the histogram stretch to blow the heck out of this thing. And you can see there's a lot of nebulosity in here. That's way down in the noise. A lot of color variation in it. And this ugly band here is caused by light coming in through the slit and rattling down through the dew shield into the sensor. We're going to fix that as soon as I can get a dew shield that's in back order. We'll get rid of that with a long dew shield, about 20 inches long. But for now, we're stuck with it. So we have a drift band down at the bottom. We have a drift band on the left. So I'm going to do the same thing I did before. Oh, we have a little bit of funny stuff up at the top too. So I'm going to, forgot that. Don't attempt to do any processing in RGB mode because it won't do it. So I'm going to give us a little extra guard band here. Unfortunately, we're going to have to cut off the very dim part of the nebula. And I'm going to minimize this satellite intrusion here. By the way, that satellite intrusion is actually a geostationary satellite. We're tracking M42. It turns out that the geosynchronous satellites cross right through M42. So if we're tracking, those objects are stationary in the sky relative to your position. If you were to take a camera, point it to that area of the sky, take a long exposure, all the stars would stream except for the geosynchronous satellites, and they would show up as a point. Kind of interesting. During the stacking operation, if you do enough stacking, this track will slowly fade out if you do enough stacking. So now we're going to crop, and that's the image we're going to play with. So what we want to do is start with background neutralization. I'm going to go back here to the hyperbolic sine, arc sine stretch. It's a much smoother and nicer image to work with. I know there's nebulosity out here, so I want to avoid that. I'll go off to the side here and select a reference point. I know there's people who've taken deep sky images over a long exposure. There's stuff out here too, but it's so far below the read noise that it doesn't matter to us at this point. It'll average out as nothing. So we're going to do color calibration. We're going to have the red band, use that selection. Green band, use that selection. Blue band, use that selection. Click neutralize background, and you can see it changed. Okay, so we're done with that. So a lot of red in the nebula. You can see a lot more of it when you're in the red band. The green band, not so much. The blue band is a lot of light pollution. And there's those halos again. Okay, so now we're going to do the background extraction while we're still on the linear mode. So we're going to go down to background extraction. Slide this off to the side. We're going to generate, again, this tolerance scale determines where these points are excluded in your image. And notice there's a lot of exclusion because of how bright that nebula is. But I know there's nebulosity here, even though there's a dark band through here. I don't want that. And I don't want that one. And I don't want that one because I know there's stuff there. And I want to get rid of these two. Oops. And there's nebulosity there, and there's nebulosity there. There, I don't want that measured, or that one, or that one, or that one. These probably not so good either. So now we've more or less excluded the nebula from this process. I don't see any stars inside the boxes because that exclusion.
What about in that one, just maybe 5 from the right and 1 row up in the bottom right of the image? Is that star an issue? Right up above that, up.
Here?
Just one down, yeah, right there, to the left a little bit.
This?
To the left, one
sorry.
more row. Yeah, and then down,
This one?
that, the one right next to that.
This one.
Yeah, that one. It looks like there's a star there. I don't know if that would be an issue or not. I was just
Probably
curious if
not,
it would.
but I'll take your advice and remove it. And I'll remove this one because there's a band of nebulosity down there too. Yeah, there was a star there. You can see it now. Good catch. Okay. Any other comments? Oh, wait a minute. I'd like to get rid of this one too because I know there's nebulosity there. Okay, here we go. Apply. Not anything noticeable there. We know that because of the way this thing does the background subtraction. At least it gets rid of the gradients. You saw a lot of gradient in there. And let's go back and just put the histogram stretch on there again. Now it's a lot less gradient in there, even though there's a halo around here, partly because of how we selected things for the background extraction. But this is down into the read noise anyway, so I'm not going to worry about it. And the color is a bit more neutral. We can do another background neutralization if we want, but let's do a little stretching before we do that because that will impact what we get. This is such a bright image that it's going to be unnecessary to pursue that any further. So now we go to histogram transform and we play the same game we did before. Pull this off to the side just a little. And we do the same thing here. Pull this over and come a little touchy. This oversized cursor is driving me crazy. All right. So we still left a little bit of light pollution in there, or I should say bias in there. So we apply, it goes back to linear. Again. And we see a little separation here in the histogram. This could be caused by the colors that are actually in the nebula at this point. So I don't want to go and do a color neutralization unless I start seeing stuff in the absolute background here. We apply this. Go and move this one a little bit further. Stop short of the green. And we're getting close to the point where we're going to run out of dynamic range. You can see the blue is inside the red. That's expected because we have a lot of H alpha here. You can clearly see the red. And there's also oxygen 3 in there. That's in the blue-green. So that would be, it's at the blue here. You can argue there's a bit more green in there, less green in there than there should be, but I think it should be okay. At this point, I'm going to decide not to stretch anymore. We'll do the rest in GIMP. Okay. You can make your choice and decide whatever you want to do, but I like to be able to do as little as possible here in SiriL, so I can have a more nuanced control in, I forgot to set them. Hold on a second. Let me set this. Okay, set the working directory again, just to be sure. Okay, so we're done with this. I'm going to save the image as M42. And we're going to say SiriL. And I just assume that it's the standard save, standard processing in there with the color neutralization, the background extract, and then histogram run. And I'm going to save this as a TIFF file. So down here, I'm going to select the file format again, TIFF, and save. And I'm going to save it as 16 bits as I did before. And there it is. So now finished with this. And we go back to friendly GIMP. If you got enough memory, you should leave GIMP running because it takes a long time to load if you're coming off a hard drive. So it's good to just leave it running in the background. So we're going to open. And here's M42, open. Again, convert. And then we're going to fit in the window. And there's what we've got. And you can see the background is not completely dark. And so, and there's no more to crop out of here. I don't think you want to play around with that. We've already cropped off some of the faint nebulosity at the bottom. So now I'm going to go to the curves. And let's play that a little bit here. I'll put this off to the side a bit. First, I'm going to drag the dark point over just to the left of the histogram. And then I'm going to pick up an adjustment point right here, and I'm going to bend it up just a little. And you can see there's just a tad reddishness in there. And that, to some extent, represents the extended redness that's in that whole nebulosity complex. If you have seen some really deep sky images of M42, it is full of H2 stuff. So if I turn this adjustment off, you can see what we started with, and we got this where it is. So I'm going to select OK. And then I'm going to remove some of that background. Oh, by the way, let's take a look at the stretch the blazes out of this thing, brightness wise, and look at there's a lot of noise in there. So I think before I do any more processing, I want to do another median blur. I use 3 pixels in most of my median blur processing. There are cases, and you'll know it when you see it, when that's too much. Because if you see it attack faint stars, it's, you need to make it a little bit less. And you watch this star right here. This is a fairly faint star. Watch when I take this off. It dimmed it a bit when I applied it. Right on the threshold of where I'd want to maybe not run it 3, but 2. But I'm going to leave it alone because I'm going to do one more small adjustment, and that'll be it. So we're going to let that go. And now we're going to fit in window. I will select levels, And you see, here's the histogram. We still have a little bit of background here. I'm going to select this and move it. And watch this faint image, make sure it doesn't go away. And it's still there. So it just touches the left edge of the histogram. Again, let's look at it with and without the adjustment. So it's a nice darker background. That's as far as I'm going to take that. I think if I stretch it anymore, we'll start to bring up. Well, let's just do it. We'll just for trial. If now, see, here's the dark point. It's at the left edge of the histogram. I'm going to pick this thing up right here and stretch it a bit more. This is all in the noise. Yes, it's red nebulosity. Yes, it should be there, but it's pretty noisy. And I opt to not do that. You can do what you want, but you can see what it does. It does bring out more faint nebulosity, but we're only working with 10-second sub-exposures, and that's pushing it a bit, in my personal opinion. So again, it's up to you. And this is where I would stop if it were me with this thing. So then we would, again, do what we had done before. We're going to export this as a Gimp processed. Again, as a TIFF file. So we'll leave the default format and export. Again, no compression. So now we go back and look at the files we've saved. Wrong one. Oh. So here's the last Gimp image. And this is what we came back from SiriL with. So we've enhanced it just a bit. We again have the halos around the stars, but I already explained what you can do about that if you want to play with it. If you have a really good optical chain, like a apochromat with a triplet or even a quad, those halos won't be there because it will have been optically corrected out. You still might want to mask the bright stars because they will bloat anyway as you do this stretching. So that's another thing you might consider. Even if you've got the best optics you can get, you may want to go ahead and mask out the brighter stars so they don't get quite so nasty in the final result. That's M42. And we have gone through an hour and a half. I hope people are still awake. Any questions at this point?
Oh, that's amazing. Never occurred to me that, well, I've learned a lot about adjusting that dark point now.
Yeah, the dark point is a powerful tool, but you can abuse it. So that's why I give you the urge to take it a step at a time, a little bit and a little bit, and watch the histogram develop so you can see where things are. And as you get further into the histogram stretch, you realize that most of the stuff in the left half of the histogram is remnants of the light pollution noise or the light pollution brightness. And as long as you don't push it too far, you can preserve most of the nebulosity.
What's the
Granted, that's burned out, but that's, by the way, there is a way to process this M42 image as it is. You can take that image before we did any stretching on it, after we did the color neutralization, the background subtraction, and take that image and save it, because that preserves more of the details right here. And then you can use some gamesmanship you can play in Gimp to overlay the less stretched image into here and blend it so that this and this blend together more smoothly. That's a lot harder process to do than what we have just done. I didn't take us through it because I didn't want to overly complicate this whole thing. It's bad enough as it is. But this is the basics. Again, I emphasize this is one way to do it. The basic idea is there. As you do this, you will find your own way, and you'll do a workflow that suits your particular image. This workflow that I described pretty much worked for the Garvey images. It's a little bit different for my backyard image. Not much, hardly noticeable what the differences are in terms of the process. But that image involves a whale of a lot more pixels, 61 megapixel camera. And so it's a little bit more challenging with that, especially with respect to memory available. The ASI 071 camera we have at Garvey is 16 megapixels. That's about typical of an APS-C frame. In fact, that camera chip is actually the same camera chip that's used in, I think, one of the Nikon APS-C cameras. And so one of the things about ZWO and QHY is they are not using any camera chips that are specialized. They are taking camera chips that were built specifically for DSLR use and adapting them by not allowing any processing on the data coming off the camera sensor and preserving the original image as a raw image. Even, I can tell you this from experiment, you cannot completely turn off processing in a DSLR. And one of the most notable examples of that is back in 2016, when I started this business with background subtraction. I thought, well, let's see what happens to the image of the dark field image that we take for calibrating out the thermal noise, because the DSLR does not have temperature control. It has a thermometer in the sensor, but no way to control the temperature. The ASI 071 and all the astro cameras that have kind of the upper end of the capabilities have a cooling device in it, a thermoelectric cooler that sets the sensor temperature lower than ambient and keeps it set there within a degree or two. Okay. And that sets a baseline noise that can be calibrated out to some extent. That's why you take your dark frame image. What I found out with the DSLR was I instructed the camera to save the raw image. I thought it was raw image with zero processing. That's what I was given to think based on stuff I could find out about the camera. That is not the case. I took some dark frames ranging from 1 second and 2 seconds and 4 seconds and 8 seconds, et cetera, and steps factors of 2 from there all the way out to an hour, just for fun. And I took all those images and I used a image analysis tool to see what happens to the, hold on a second, I forgot to disable the stupid phone. All right, I'll catch that later. I know who it is. And what I found was, much to my surprise, the camera was making corrections for the longer exposure. There's an equation that defines for every camera sensor how much the thermal noise grows as the exposures increase in length. That's built into the processor inside the camera that the camera manufacturer puts in there to manipulate the image so that you get the best image you can for the general photography world. Okay. For astrophotography, that's a problem because for that 1 hour exposure, I had only slightly less thermal noise than I expected from a 10-second exposure. And that's not right. So they manipulated the image in a way I didn't want to do. And there was no way to turn that off. So That's what you're dealing with. Fortunately, it's not a disaster. You can live with it if you're going to use a DSLR, but be warned, there's some secret processing going on in there that you don't want. And the cameras that are built for astrophotography don't do anything to the image. It simply shoves it out into your hard drive, and you can contend with it from there. So any more discussion, questions? You want to pursue anything else?
Sure. A couple of questions. One, you're using curves to adjust the dark point. Could you do the same thing with levels?
Yes, you can. I didn't do that because that's just my processing style.
Okay. And when you're doing the curves, you have the option of adjusting each color separately rather than RGB altogether. Is there any advantage of doing the colors separately?
There shouldn't be, because you've done the color background neutralization step in SiriL.
Mm-hmm.
There shouldn't be any serious color imbalance there. But I personally would not do that, because if you adjust everything in the individual color bands, you can change the overall color balance in ways that you don't really want to do. And it may not be obvious until you get pretty far down the line. You realize, oh, that is really not what I wanted.
Okay.
So I'd avoid doing that. But yeah, if you get to a point where you've done some stretching and you realize that there is some residual color bias in the background that you want to preserve, because you want some more of this nebulosity out here preserved, out in the outer edges here, then you might want to manipulate some of the color here, because you saw the histogram, you saw the slightly reduced green in the histogram.
Mm-hmm.
And that can cause some color biasing in this part of the image, which you may not find pleasing. I'm not unhappy with this color. You might be, and you can process it any way you want.
Mm-hmm. Okay, thank you.
Anybody else?
Well, Vance, on this one in particular, where you have such great colors, would you change anything on the saturation like you did?
Oh yeah, I would do that too, but I didn't right for this, but I would like to have it a little more saturated than this. We can do that right now. I mean, it's hue and saturation, do a little saturation boost here. You see what I did? Here's removed. I could argue that that might be what you want. So, I mean, that's okay. If I don't like it, I can always get rid of it by going over it and go back to the previous step. I mean, that's the nice thing about Gimp and Photoshop and all these tools. It preserves all of the adjustments that you've done. And you can go back and back in time and get rid of everything. You know, here's what curves did. Here's what the medium blur did. Here's what the levels did, etc. So you can go back and change anything you want. Because if I go back here, I'm free to change everything from here on if I want to. So I've not lost everything. You can see some of the faint red nebulosities in the extreme edges here. I choose not to preserve that, and I choose not to try to pull that out, because it only brings up noise that I can't control anyway. And to apply another round of median blur will only get rid of these very faint stars, and I don't want to do that. That's my personal preference.
Gotcha. Thanks.
Thanks, Vance. That was really awesome.
So I hope it's useful, and I hope people will take advantage of it. It's a good way to get started. If you get really hooked into this thing, then there's other tools you can get that give a bit more flexibility, but it's a bit more complicated to work with.
What was the name of the tool that you used for the multi-level contrast?
Oh, that's Astro Image. I'll
Astro
show you the icon here.
Okay, Astro Image. Okay, got it.
And Astro Image is a general purpose image processing tool. It's not intended necessarily specific to astrophotography. But boy, does it have powerful enhancement tools. There's a long list of tools here that you can play with, including unsharp mask and wavelet processing. I tried that on that M1 image, and wavelet processing produces dark circles around the stars. I don't like that. In fact, wavelet processing on planetary images suffer from that kind of problem. It creates artifacts you don't want. But so you have to be very careful with it. After experimenting around, I found this multi-scale contrast tool was in fact a stripped down version of wavelet processing. And it gave a little more nuanced result, as you saw. The downside
there
is
was
it's not a free tool. It cost you $42 for a license. Not a pocketbook breaker, but if you don't want to spend any money, then don't. I found this to be useful for general world photographs too. I like this tool because I can do what I want in Gimp, but Gimp does not have these enhancement tools. So I found this to be very helpful.
Cool.
All right. Anything else? We're
No,
coming-
thank you, Vance.
Thank you. This has been great.
If you want to do anything else, that's fine. I don't think we have time to process the M31 image. But if you want to do that separately, just to see an example, I'd be happy to do that. But I think we ought to, we've been at this over an hour and 20 minutes. So that might be the end of people's patience.
Okay.
So this goes up on our website, I mean, on the YouTube site?
Yeah, it'll take about maybe an hour to render, and it'll be available on the website. So or on not our website, it'll be available on YouTube,
YouTube channel, great.
our YouTube channel. And I'll go after it's rendered. I'll go ahead and put a little thumbnail in front of it so you can see it.
Cool,
Great.
great.
Well,
Well, I'm
one
gonna
thing, if
take
you
off
asked,
and-
it'd be helpful to be able to go through this if you wanted to, again, with the YouTube process. It's covering a lot.
I missed a couple of things on the way, so I got behind. I couldn't keep up. So it would be nice to go through.
Yeah, I'm
it.
sorry about that. I didn't mean to do that, but I'm
No,
just-
no, it's not. It's better to do that and get all the way through it because we can go back and look, like the thing that I missed, I'll go back and find it and see, oh, okay, that's what that was. So, no, it's fine. Rather than stopping you and, saying, what, I missed something,
Okay.
let you go and get the whole thing. It's much
Yeah.
better.
Yeah, this has been great. Thank you.
Thanks, Vance.
Thanks, Vance.
If we needed
Thanks a lot.
an update on this, I'm happy to push it a little bit further. So if you have experience with this and you want to get a little further with it, I'd be happy to do another, adding more levels of processing. But this, as you can see, this will get not too bad images from the Garvey site. And that, I'm more than pleased, even though the images are noisy. You saw what the sky is like there. This is what you can do almost anywhere in Southern California in the urban light pollution.
It's magic, Vance. It's just magic.
Well,
There's no
now
magic here. There's no magic here, I promise you.
I'm going to burn a lot of time going back and reprocessing a lot of my images now.
I find myself doing that too. I went back and looked at some of my old images to go back through them with SiriL to see if I could do as well with SiriL as I did with PixInsight. And I was hard pressed to tell the difference.
Very cool. I'm going to take off, guys. Thanks a lot.
All right.
All right.
Are we all finished here?
I think so.
Okay.
All right. Thank you, Vance.
Well, thank you.
Good evening.
Thanks.
All right. I'm going to be ending it now. Okay.